Hello and welcome to another session where we are going to look at a topic in Form 2 Physics. This topic is magnetic effect of electric current. One of the effects of electric current is that it can cause heating, as when we use it in a heater. It can also cause magnetism, and there is a vast application of this particular effect in our everyday life situation. Let's have a look at some of these effects. You've encountered the electric motor. The electric motor is one of the applications of the magnetic effect of electric current, and it finds application in very many devices, including electric drill. You may have this blender here, electric blender. You may have the drives in a computer, the disk drives in a computer. In industry, they are used in lathe machines and very many other applications. This one is an electromagnetic relay. We'll be looking at some of these applications later on, involving loudspeakers, involving electric motors, and so forth. Even the television set uses magnetic effect of electric current. Now, we'd like to start with a simple experiment whereby we want to show that there is a magnetic field around a conductor which is carrying current. And maybe that is one of the statements that you might want to write down. After you write down the topic, magnetic effect of electric current, in capital letters, then down there you can write down this statement that there is a magnetic field around a conductor which is carrying current. In other words, we have a wire, such as a circuit like this one. When we switch on, there will be electric current flowing through this wire from the positive side of that battery through this gadget here, which we refer to as a rheostat. We are going to look at its function. Then from there, we move over to this switch, and then there is this straight wire, and then it's connected back to the negative side of that battery. The function of this gadget here, which is referred to as a rheostat, is to vary the amount of current flowing through this wire. Another function that it serves is to avoid short-circuiting the terminals of this battery, because if we know we just connect a wire from here and then we bypass the rheostat, we move like this and back to the negative terminal, we will be short-circuiting the terminals of the battery, and that will spoil the battery. So it serves two functions: to avoid short-circuiting the terminals of the battery, and at the same time control the amount of current which flows through this particular circuit. We can have an ammeter here which will help us to measure the amount of current which is flowing through this wire. This experiment was done by somebody refers to as Hans Onsted long time ago. He was the first person who showed that there is a magnetic field around a conductor which is carrying current. Now, how do we detect a magnetic field? We need a magnetic compass. A magnetic compass consists of a magnetic needle which is suspended lightly in such a way that it is affected by the Earth's magnetic field. So it always points in the north-south direction. So we are going to align this wire in such a way that the pointer of the magnetic compasses are pointing in the north-south direction. In other words, this wire should be arranged in such a way that it points in the north-south direction. Remember, it's not carrying current yet. There is no current in it because the switch is off. But the needles of the magnetic compass are already pointing in the north-south direction of the Earth because they are detecting the Earth's magnetic field. Now, let's see what happens when we switch on. So let's close this switch here, and after some time, that is what we are going to observe. There's something else which I should have pointed out in this slide. The first magnetic compass is put above the wire. The second magnetic compass is put below the wire. And now, when we switch on, this is what we are going to observe. Let me just go back there. We switch on. Current is now flowing in the wire, and we notice that the magnetic compasses deflect. The reason why they deflect is because they have detected a second magnetic field. Other than the magnetic field due to the Earth, they have detected a second magnetic field. And this magnetic field must certainly be due to the current flowing in the wire, because if we switch off, they revert back in their original position. That is, they will point along the wire. And again, when we switch on, they deflect. That shows that if there is a current flowing through that wire, then there is definitely a magnetic field around that wire, and that magnetic field is strong enough. It is stronger than the magnetic field due to the Earth, and that is why it overcomes the magnetic field due to the Earth and causes a deflection. So this simple experiment can be used to show that there is a magnetic field around a conductor which is carrying current. There is a magnetic field around a conductor which is carrying current. What is the direction of this magnetic field? First of all, what will happen if we increase the amount of current in the circuit? And that is where this rheostat comes in. It helps us to change the amount of current flowing through the circuit. We reduce the resistance by moving this terminal this way. So when we move this terminal this way, it's going to reduce the resistance in the circuit, and that will make sure that more current flows in the circuit. And what do you expect will happen with the deflection of the magnetic compasses? Of course, there will be more deflection. So that's exactly what we are going to do. If we increase the magnitude of the current, let's see what happens. There is certainly more deflection. The second thing that I want you to observe is that the magnetic compass above the wire points downwards, while the one below the wire points upwards. At least for the screen, that is what we are going to have. But if you're doing the experiment on a table, you'll find that the magnetic compass around the wire may point towards you. The one which is below may point away from you. That shows that the direction of the magnetic field above the wire is different from the direction of the magnetic field below the wire. Remember that. They point in opposite direction, and that is evidence that the direction of the magnetic field lines below the wire and above the wire, they are different. They are in opposite directions. That is very, very important. The other thing I'd like you to observe is that the magnetic needle always points in the direction of the magnetic field lines. The magnetic needle always points in the direction of the magnetic field lines. What is a magnetic field? Perhaps at this particular point, I want to pause this slide and we move over to some questions. I'd like us to look at some of the questions that we have here. What is a magnetic field? That region around a magnet where a magnetic force is experienced is referred to as a magnetic field. We are going to give that very simple definition rather. That a magnetic field is that region around a magnet where a magnetic force is experienced. So let's see the answer to that particular question. So over here, the region or space around a magnet where magnetic force is experienced is a magnetic field. So you might want to pause the video and write down those questions and the answers as we discuss them. So let's hide that answer, because later on I'm going to ask you the same questions. So let me hide the answers. Let me go to the second question. How is magnetic field represented on paper? Do you remember that we have already done this topic, magnetism? We have already covered the topic, magnetism, and we looked at a bar magnet. And from time to time, you are asked to draw the magnetic field around a bar magnet on paper. You'll remember that we use magnetic field lines. So a magnetic field is represented on paper by magnetic field lines, or using lines of force, magnetic lines of force. That is how we represent a magnetic field. Again, let me hide that answer. There's something else that we did when we are looking at magnetism, and these are the properties of magnetic field lines. How many of them can you be able to state right now? The fact that they point from north to south, they don't cross each other, they behave like stretched rubber bands, and so forth. There are very many properties of magnetic field lines. Let's refresh our minds and see what are these 5 important properties of magnetic field lines. Of course, the first one, we have already talked about it, is that they point from north to south. Number 2, they leave and enter a surface at 90 degrees, that is normally. They never touch. They neither touch nor cross each other. This word here should be neither. They neither touch nor cross each other. Number 4, they behave like stretched rubber bands. That is, they possess longitudinal tension. Number 5, lines of force are parallel to each other and pointing in the same direction, always repel each other sideways. In other words, they possess sideways repulsive forces. Again, these are facts that we have already encountered when we looked at magnetic field. Okay. Now the next question is about, it shows a conductor carrying current into the paper, and we are required to draw several lines of magnetic field lines around that conductor. It is at this point that I want to go back to the slides. This is where we were, and we are saying, now that we know that when we switch on the current, there is a magnetic field around this wire, and it is evident that this is so because the magnetic compasses deflect. And when we increase the current, that magnetic field becomes stronger. That is why there is more deflection. In other words, you may be asked a question like this: what observations do you make when the current is increased? You will observe that there is more deflection. Then, what conclusions do you make from that? You will conclude that the magnetic field becomes stronger. Let's continue. How about reversing the direction of current through the wire? What is the effect of reversing the direction of current through the wire? And how do we reverse this current through the wire? Number 1, we interchange the terminals of the battery. This wire in our previous diagram was here, and this one was here. In other words, current was flowing. Let me just go back to that particular slide. Current was flowing this way via the rheostat, and it was flowing from my left all the way to my right. That is how current was flowing. In this new setup, we have just interchanged the wires such that the one which was here comes here and the other one goes there. In other words, we have reversed the terminals of the battery. How do you reverse current through that wire? By interchanging the terminals of the battery. That is how you do it. So what is the effect of that? What is the effect of reversing the magnetic field through the wire? Let's see. Remember, in the previous demonstration, this pointer pointed downwards, while this one pointed upwards. What is the effect? of reversing the direction of current through the wire. You have seen that when you do that, the pointers are going to point in opposite directions. The one which had pointed downwards now is pointing up. The one which had pointed up now is pointing down. And remember, the pointer of a magnetic compass shows the direction of the magnetic field lines. The direction of the pointer of a magnetic compass shows the direction of the magnetic field lines. So we can tell that since the deflection of the pointers of the magnetic compasses has been reversed, the magnetic field lines has also been reversed. That is the conclusion we make. So if you reverse the direction of current through the wire by interchanging the terminals of the battery, you're going to reverse the direction of the magnetic field around the wire. Now let's go ahead and try to draw that magnetic field around the wire. Now let's look at a conductor such as this one here. Let's assume this pen is a conductor and current is flowing in this direction. The magnetic field consists of concentric rings around the wire. That is one ring inside another one. Concentric rings around the wire. So if the current is such that now it is coming towards you, the concentric rings are like this. You can just imagine that there is a ring around this wire like this, and that will be a magnetic field line. When the wire is like this, then we draw it like this. If it is in 3 dimensions, like for example, what I've drawn here is in 3 dimensions. Let's see whether we can use a simple rule to determine the direction of these arrows. The current is flowing in this direction, from this point to this direction like this. So imagine that is a conductor, it's pointing in that direction, and now I'm going to hold the conductor in my right hand with my thumb pointing in the direction of the current through the conductor, and my fingers will show the direction of the magnetic field. I'm going to repeat this. We want to determine the direction of the magnetic field around that conductor which is carrying current. The first thing you do is to identify the direction of flow of current through the wire. It's flowing to the right, like that. Then I'm going to hold the wire in my right hand in such a way that my thumb points in the direction of current in the wire. My fingers will automatically point in the direction of the magnetic field. And that is exactly what you have in that diagram over there. So practice using that. It's called the right hand grip rule. Let's continue and see what else we can learn. So that is a previous demonstration whereby current now is flowing in this direction. You can see that these arrows above this concentric ring, if you look at this particular section here, you will be able to see that this part of the concentric ring is above the wire, while this other part of this ring is behind the wire. In other words, if this is the conductor and I'm looking at a ring which is here, there is this part of the ring which is above the wire, and as far as I'm concerned, there is this other part which is behind the wire. That is exactly what we have here. So when you draw these concentric rings, remember to break this point here so that you can show this part is behind the wire, while while this part is above the wire. And then we put arrows on this side, or on this side, or even here, anywhere, so long as the direction of the magnetic field is correct according to the right hand grip rule. Let's see what else we have here. Remember that first statement that there is a magnetic field around a conductor carrying current. It's a very powerful statement, and I had asked you to write it down. Now I'm repeating. There is a magnetic field around a conductor carrying current. The magnetic field lines are in the shape of concentric rings around the wire. The magnetic field lines are in the shape of concentric rings around the wire. Let's study this diagram here. First of all, the dots, the moving dots, they show the movement of electrons in the conductor. The conventional direction of current is opposite to the movement of electrons. I want to repeat that. That is very important. If you know the direction of movement of electrons in the wire, because the rate of flow of charges is electric current, if you know the direction of movement of electrons in the wire, you should know that the opposite direction is the actual direction of flow of current. So current, the electrons are moving downwards as far as this blue conductor is concerned. As far as this blue wire is concerned, the electrons are moving downwards. So electric current is represented by this yellow arrow pointing upwards. And that is where now you come and the conductor is like this. You grip it in your right hand like that with the thumb pointing downwards, and you can see that the magnetic field is exactly the way I have drawn it here. The magnetic field lines direction is exactly the way this one shows. So these concentric lines, they show the magnetic field pattern because the lines themselves are magnetic field lines. So the field pattern is in the shape of concentric rings around the wire. So the flow of current is as shown by the arrow, and it shows the movement of flow of positive charges. Although we know positives do not move, it's electrons which move, but the opposite direction to the movement of electrons is what we refer to as flow of current. Remember that. So that diagram is very, very important, and I'd like you to understand every aspect of it. Let's continue and see what else we have here. Of course, here I'm trying to emphasize the right hand grip rule. That diagram, you'll find it in your textbook, and it shows a right hand being used to grip a wire with the thumb pointing in the direction of the current in the wire. The fingers are going to point in the direction of the magnetic field. Like that. Very, very simple. Let's continue and see what else we have. Here we've got two conductors carrying current in opposite direction. And maybe we're going to pause at that point and move back to the questions. Remember, there were questions that we were trying to answer here. Let me get these questions here. And we have the figure below shows a conductor carrying current into the paper. Let me explain this. When this is the conductor, that right now it's horizontal and it's carrying current from my left hand side to my right hand side. It's carrying current in that direction. If it faces me, then current is coming towards me like this. If it faces you, current is going away from me. So when we are talking about a piece of paper, it is your book. How would you represent current moving into the paper, current moving away from you? We usually use a small circle and an X. When current is facing is coming out of paper, then we usually use a small circle and a dot. A small circle and a dot. So let's see how that diagram looks like under the use of the right hand grip rule. This is the diagram over here, and here we have it. There. You can see that dot, that circular, it is the cross-sectional area of the conductor, because the conductor has got a circular cross-section. It's a wire. Current is moving into the paper, so it's represented with an X. This is the first magnetic field line, the second magnetic field, the third magnetic field. Point number 1 is the direction in which those arrows point. So I'm going to grip it like that, and I'm going to point into the paper like that. And you'll be able to see that when the thumb points into the paper, the magnetic field is clockwise. It's clockwise. You can see that. Clockwise. Of course, when now it's current out of paper, I'll point upwards like that. Okay? Thumbs up. Upwards like that. The right hand grip rule is like the thumbs up that we use when we want to appreciate something. Okay? Thumbs up. So if it is out of paper, I hold the conductor. Imagine I'm holding the conductor with the thumb coming out of paper. When I look at my fingers, they will be pointing in the anti-clockwise direction. But when it is into the paper, it is clockwise direction. A very simple rule, the right hand grip rule, can help us understand that. So that is the first point. Knowing what this symbol represents, a circle and an X represents current into the paper. The second thing is the use of the right hand grip rule to identify the direction of the... Okay, first of all, it's to draw the magnetic field lines around that conductor. There are a few points that you need to pay close attention to. The distance from the conductor to the first line is this much. But the distance from this magnetic field line to the next one is a little bit larger than this distance here. And then this one is larger than this one here. And then this one is larger than this. In other words, the distance between neighboring concentric circles increase as you go away from the wire. That shows that the magnetic field is becoming weaker and weaker as you move away from the conductor. So observe those points. I've put those points here, and they're the ones which ensure that you earn these 3 marks. So concentric circles around the conductor, you should be able to draw those concentric lines around the conductor. They have arrows pointing in the correct direction. Use of the right hand grip rule. Use of the right hand grip rule. That is how you know how to put this arrow. Number 3, the space between the lines increase outwards, showing the magnetic field becomes weaker as the perpendicular distance from the conductor increases. In other words, this is the conductor. As you move away from the conductor, that magnetic field becomes weaker and weaker and weaker and weaker. In other words, it's very strong close to the conductor. Understand that. Let's see whether there is any other point. I don't think there is another point as far as that particular question is concerned. So what have we been able to learn in this topic? This is what we've been able to learn in this particular topic, that there is a magnetic field around a conductor which is carrying current. This magnetic field is in the shape of concentric rings around the wire. The distance from one concentric ring to the next one increases as you move away, as the perpendicular distance from the wire increases. That shows that the field becomes weaker as you move away from the conductor. we've also been able to see that the direction of the magnetic field depends on the direction of the current through the wire. If you reverse the direction through the wire, the magnetic field is immediately reversed. When we are looking at a conductor carrying current, if it's carrying current into the paper, what kind of symbol do we use? We use a circle and an X. If it's carrying current out of paper, we use a small circle and a dot at the center. And then, of course, use the right hand grip rule to determine the direction of the magnetic field lines around the conductors. So go through the video once again. Try answering those questions that we have already looked at without now referring to the notes all the time. That is what you do when you learn something new. You try to read it. Once you have read it and you know it, you cover the answer, and then you try to test yourself. Can I still be able to remember this thing? You know, it may appear to be a little bit odd. Like, for example, if you're in a room all by yourself, what you can be able to do is try this, is to read your notes, loudly. Read your notes loudly. Listen to your voice as you read the notes. That one is a technique that works wonders when you want to remember some of the facts that are a bit of a problem. Repeat that process several times. Chances are that in a test, what you will hear is your own voice when you are doing the exam. Okay? And of course, when you're practicing this, don't practice in the presence of the other students, because you'll be making noise in the classroom. I'm talking about maybe you're all alone, maybe at home in your own room, or maybe in a field, and you're trying to recall a few points here and there. Read them aloud. The second thing that you can do is to cover up the answers. You get a piece of paper, you put it above the answer so that you don't see the answers as you read the question. Read the question, cover the answers, and then briefly look at the answers, read the answer, then cover it again and see whether you can be able to remember it. It's a technique that works wonders. Use it several times, and when you encounter a new concept, if you use that method several times, you are likely to remember the exact points. In the next lesson, we are going to look at other aspects of this particular topic. So, see you in the next lesson.